From the moment our ancestors first looked to the heavens, a singular persistent question has echoed through the ages. What lies beyond the horizon? This impulse, this insatiable curiosity, is woven into the very fabric of our being. It drove us from the savannas of Africa, across vast and treacherous oceans, to every corner of our terrestrial home. It pushed us to pierce the thin veil of our atmosphere, to leave footprints on the dusty surface of another world. Our history is a chronicle of transcending boundaries, of turning the impossible into the accomplished. We are a species defined by our reach, forever striving for the next shore. And as our knowledge has grown, so too has the scale of our ambition. Our telescopes, instruments of profound revelation, have unveiled a cosmos of breathtaking grandeur. They have shown us that the familiar stars of our night sky are but a handful of sand on an immeasurable beach. Our sun is just one of hundreds of billions of stars, all bound together by gravity in a colossal swirling spiral of light and dust. We call it the Milky Way, our home galaxy. But the most staggering revelation was yet to come. Looking deeper into the darkest voids between the stars, we found other lights, faint, ethereal smudges. For centuries we believed them to be mere clouds of gas within our own cosmic city. Then we understood. These were not clouds. They were other cities, other galaxies, island universes, each one containing billions, perhaps trillions, of their own stars, their own worlds, their own possibilities. The Andromeda Galaxy, the Triangulum Galaxy, the Sombrero, the Whirlpool. An endless archipelago of light scattered across an ocean of absolute blackness. And with this realization, a new horizon was born. A new dream took hold in the collective human imagination. To one day cross that ultimate ocean. To sail the void between the galaxies and set foot on a world orbiting a star in a completely different cosmic realm. This is the grandest voyage conceivable. A journey that would dwarf every expedition that has come before. It represents the final, triumphant act of human exploration. But a dream, no matter how potent, must eventually contend with the unyielding laws of reality. The universe is not a passive stage for our ambitions. It is an active, evolving entity with rules that cannot be broken. And when we examine the chasm that separates us from those neighbouring islands of light, we are confronted by a series of barriers, each more formidable than the last, each a great wall standing between humanity and its ultimate dream. These are not mere technological hurdles to be overcome with time and ingenuity. They are fundamental constraints, woven into the very fabric of space-time, of energy, of life, and of the cosmos itself. And together, they deliver a profound and perhaps sobering verdict. A decree that our destiny, for all its potential grandeur, is forever bound to the shores of our own galactic home. This is the story of why, for all our courage and all our genius, humanity will never escape the Milky Way. The first Great Wall, the most immediate and comprehensible, is one of pure soul-crushing scale. We are accustomed to large numbers, but the distances involved in intergalactic travel render our familiar units of measurement utterly meaningless. To say that the Andromeda Galaxy, our closest major galactic neighbour, is 2.5 million light-years away is a factual statement. It is also an abstraction, a number so vast that our minds, evolved to gauge the distance to the next river or mountain range, cannot truly grasp it. We need a different frame of reference. Let us shrink the entire colossal Milky Way galaxy, 100,000 light-years across, down to the size of a large dinner plate. On this scale, our entire solar system, from the Sun to the orbit of Neptune, would be much smaller than a single grain of salt. The Voyager 1 spacecraft, our most distant emissary, which has been travelling for nearly half a century, would have barely moved from the centre of that grain. The entire history of human civilization would have unfolded in a space tinier than an atom. Now, on this scale where our galaxy is a single dinner plate, where is the Andromeda Galaxy? Is it on the other side of the room, across the street? No. The Andromeda dinner plate would be located more than 25 metres away. Imagine standing in your home, holding this plate representing everything we have ever known, and seeing the next plate resting on the far side of a public swimming pool. Between them lies an emptiness so profound, so complete, that it makes the vacuum of interplanetary space seem crowded, and Andromeda is our closest companion. The Triangulum Galaxy, the next in line, would be a slightly smaller plate nearly 30 metres away. Most of the other galaxies we see with our telescopes, those myriad smudges of light, would be other dinner plates scattered across entire continents. The Virgo supercluster, our local galactic neighbourhood, would be a collection of plates spread across a small country. This is the arena of our ambition. It is not an ocean to be crossed. It is a void of such terrifying magnitude that it challenges the very concept of a journey. To traverse this gap is not like sailing from Spain to the New World. It is like an ant in Lisbon attempting to crawl to a specific grain of sand in the middle of the Gobi Desert. The sheer empty space is the first and perhaps the most brutal filter on our aspirations. It is the universe quietly telling us the scale of our confinement. The knowledge of this confinement is a relatively recent development. For most of history, we believe the Milky Way was the entirety of creation. The great philosophical and scientific debate of the early 20th century, between astronomers Harlow Shapley and Heber Curtis, centred on this very question. Shapley argued that the spiral nebulae, like Andromeda, were part of our own galaxy. Curtis contended they were distant island universes. The matter was settled in 1924 by Edwin Hubble. Using the powerful Hooker telescope on Mount Wilson, he identified a specific type of pulsating star, a Cepheid variable, within the Andromeda Nebula. These stars have a unique property. Their brightness is directly linked to their pulsation period. By measuring how fast one brightened and dimmed, Hubble could calculate its true intrinsic luminosity. Comparing that to how dim it appeared from Earth, he could calculate its distance. The number he arrived at was staggering, proving conclusively that Andromeda was a separate galaxy, located far beyond the confines of our own. In that moment, the known universe expanded by an unimaginable factor, and in the same instant humanity became immeasurably more isolated. We were no longer at the centre of everything. We were inhabitants of one island among countless others, separated by an impassable sea. Confronted with such phenomenal distances, our instinct is to think of speed. If the journey is long, we must simply travel faster. This leads us to the second Great Wall, a barrier not of space, but of physics itself. It is perhaps the most famous and least forgiving law in the cosmos, the universal speed limit. At the dawn of the 20th century, Albert Einstein, in his theory of special relativity, completely reshaped our understanding of space, time, and motion. He revealed that as an object with mass accelerates and approaches the speed of light, its effective mass increases. The energy required to accelerate it further grows exponentially. To reach the speed of light itself would require an infinite amount of energy. It is the ultimate cosmic red light. Nothing with mass can ever reach it, let alone surpass it. Light speed is not a target to be achieved. It is a fundamental, insurmountable asymptote. So, let's be generous. Let's imagine a future civilization capable of building a starship that could achieve an astonishing 99.9% of the speed of light, a velocity so extreme it borders on the divine. We point this magnificent vessel towards Andromeda and engage its engines. What would the journey be like? From the perspective of the crew on board, another of Einstein's strange and beautiful truths would manifest: time dilation. As you approach the speed of light, time for you slows down relative to a stationary observer. For the voyagers, the journey would be subjectively shorter, but the universe outside their window would age at a ferocious rate. The 2.5 million light-year journey would still take, from their perspective, thousands of years. But from the perspective of Earth, the home they left behind, more than 2.5 million years would have elapsed. Consider the implications. The crew would embark, leaving behind a world of familiar continents, cultures, and languages. When they arrived, if they ever looked back, everything they knew, everyone they had ever loved would be gone. Their entire species might be extinct, or evolved into something unrecognizable. The cities they remembered would be dust, buried under miles of rock and sediment, The mountains themselves would have eroded and changed shape. They would be ghosts arriving at a destination with no home to report back to. They would not be explorers, they would be relics, adrift in a future they could never have imagined. The speed of light isn't just a barrier to travel, it is a barrier to connection. It ensures that any intergalactic journey is a one-way trip into oblivion, a self-imposed exile from the rest of human history. Even this fantastical scenario, however, ignores the third Great Wall, the staggering problem of energy and engineering. To propel a spacecraft, even a small one, to 99.9% of the speed of light requires an amount of energy that beggars belief. The physics is relentless. The kinetic energy of an object increases with the square of its velocity. As you get closer to light speed, the relativistic mass increase makes the energy requirement skyrocket towards infinity. How much energy are we talking about? To accelerate a ship the size of a large skyscraper to near light speed would require more energy than humanity has produced in its entire existence. It would require more energy than a supernova explosion. We are talking about harnessing the total output of thousands of stars for an extended period. Our most powerful concepts for propulsion barely scratch the surface of this challenge. A fusion rocket, which would work by fusing hydrogen atoms together in a controlled, continuous explosion, is orders of magnitude more efficient than our current chemical rockets. Yet, even a perfect fusion drive would require a fuel tank so massive it would make the ship itself a tiny appendage. The fuel needed to accelerate to near light speed would itself require more fuel to accelerate, which in turn requires even more fuel. This is the tyranny of the rocket equation, a dilemma that becomes monstrous at relativistic velocities. Science fiction offers a more exotic solution, an antimatter drive. When a particle of matter meets its corresponding antiparticle, they annihilate each other, converting their entire mass into pure energy, according to Einstein's E equals mc squared. It is the most efficient energy source theoretically possible, but the challenges are monumental. We can currently produce antimatter only in minuscule quantities, particle by particle, in colossal accelerators like CERN, at an astronomical cost. To produce enough antimatter to fuel an intergalactic voyage would require the entire energy output of our Sun for centuries, and we currently have no known way to store it safely. A single gram of antimatter, if its containment field failed, would explode with the force of a nuclear bomb. A fuel tank full of it would be the most dangerous object ever created, and even if we could solve the energy crisis, the engineering problems are just as daunting. At near light speed, the empty space between galaxies is no longer empty. Every stray hydrogen atom, every tiny speck of cosmic dust becomes a lethal projectile. Hitting a particle the size of a sand grain at 99.9% of the speed of light would result in an impact with the energy of a massive conventional bomb. The spacecraft would be constantly bombarded by a stream of high-energy particles, like flying through a continuous galaxy-spanning hailstorm of radiation and explosions. It would need an impossibly durable shield, something capable of withstanding constant high-energy impacts for millennia. A magnetic field could deflect charged particles, but it would do nothing against neutral atoms or micrometeoroids. A physical shield would be ablated away over time. Any solution we can currently conceive of would either be too heavy to accelerate, or would fail long before the journey's end. The ship would be sandblasted out of existence. The universe, it seems, actively defends its vastness. Let us for a moment indulge in pure fantasy. Let us assume we solve the problems of distance, speed and energy. We invent a magical instantaneous warp drive. We discover an infinite clean energy source. We construct an indestructible vessel. Even with these godlike technologies, we would still face the fourth Great Wall, a barrier perhaps more complex and intractable than any law of physics: ourselves. An intergalactic journey, even with impossible speed, would last for many human lifetimes. The vessel could not be a simple craft. It would have to be a world in itself, a generational ship, an ark sailing the cosmic ocean, carrying a fragment of humanity to a new shore. The original crew would never see their destination. Their children, and their children's children for 100 generations or more, would be born, live, and die within the confines of this manufactured world. The biological challenges are formidable. The Ark would need a perfectly closed-loop ecosystem, capable of recycling every atom of water, air and waste for thousands of years without fail. A single, uncorrectable breakdown in this system would mean extinction. The inhabitants would be subject to the constant threat of cosmic radiation, far from the protective magnetic field of a home planet. This would lead to higher cancer rates and potential genetic degradation over many generations. Long-term existence in zero gravity causes severe muscle and bone density loss, so the ship would need to generate artificial gravity, likely through constant rotation, a process that would consume a tremendous amount of energy and place immense structural stress on the vessel. But the sociological and psychological obstacles are even more daunting. What would it mean to be human in such a context? The entire world of the inhabitants would be a few hundred meters of metal corridors and recycled air. The concepts of sky, rain, ocean, or wind would be nothing more than historical data, abstract legends from a mythical planet called Earth. How would a society maintain its purpose and cohesion over 1,000 generations, with a goal that none of them will ever personally achieve? What political systems would evolve? What new religions might form, centered around the ship, the mission, or the distant promised land of Andromeda? Language would drift. Cultures would diverge. The original mission directives could be forgotten, corrupted, or reinterpreted into myth. There is a very real possibility that after a few dozen generations, the inhabitants might forget they are on a ship at all. They might come to see their metallic world as the entire universe, and the idea of an outside or a destination as a dangerous heresy. The psychological pressure on each individual would be immense. To be born into a life with no choices, with a predetermined destiny to serve a ship on a journey you did not choose, could lead to profound existential despair. We are creatures shaped by our environment, by the challenges and wonders of a living planet. To remove us from that context for millennia is an experiment whose outcome is terrifyingly uncertain. The greatest danger to the mission might not be a meteor or an engine failure, but the fragile, complex and unpredictable nature of the human mind itself. The Ark, designed to preserve humanity, might become its tomb, not through physical destruction, but through a slow decay of spirit and purpose. And now we arrive at the final barrier, the ultimate and most absolute wall. Unlike the others, this is not a static obstacle to be overcome. It is a dynamic, cosmological process that is actively and relentlessly pushing our goal ever further away. It is the accelerating expansion of the universe itself. When Edwin Hubble first measured the distances to other galaxies, he also analysed their light. He discovered that the light from nearly every galaxy was redshifted. This is a cosmic equivalent of the Doppler effect. Just as the pitch of a siren lowers as it moves away from you, the wavelength of light from a receding object is stretched, shifting it towards the red end of the spectrum. What Hubble had discovered was that the universe was expanding. Every galaxy was moving away from every other galaxy. For decades, cosmologists debated the ultimate fate of this expansion. Would gravity eventually win out, pulling everything back together in a big crunch? Or would the expansion continue forever, slowing down over cosmic timescales? The answer, discovered in the late 1990s, was more shocking than anyone had imagined. By observing distant supernovae, astronomers Saul Perlmutter, Brian Schmidt and Adam Rees found that not only was the expansion continuing, it was accelerating. Some mysterious, unknown force was acting as a kind of cosmic anti-gravity, pushing space-time itself apart at an ever-increasing rate. We call this force dark energy. This is the final, non-negotiable decree. The very fabric of space between us and other galaxies is stretching, and the farther away a galaxy is, the more space there is to stretch, and thus the faster it appears to recede from us. This has a profound consequence. There is a cosmic horizon, a point of no return. Galaxies beyond a certain distance are already receding from us faster than the speed of light. Not because they are travelling through space that fast, which is impossible, but because the space between us and them is expanding so rapidly that even light cannot overcome the gulf. We can never reach them. No matter how fast we travel, no matter what technology we invent, they are gone forever. And because the expansion is accelerating, this horizon is getting closer. Galaxies that are reachable today will not be reachable in the distant future. The universe is, in a very real sense, closing off. The number of destinations available to us is constantly shrinking. Our local group of galaxies, a small collection including the Milky Way and Andromeda, is bound together by gravity. We will eventually collide and merge with Andromeda in about 4.5 billion years, forming a single giant elliptical galaxy some have nicknamed Milkomeda. This galactic merger will be our entire intergalactic future. This small cluster is our cosmic neighbourhood, and we are gravitationally locked inside. Everything else, every one of the other 2 trillion galaxies in the observable universe, is being pushed away by the relentless tide of dark energy. We are living on an island, and the ocean is not just vast, but actively growing, carrying all the other islands away from us in an accelerating exodus. Over the truly long-term future of the cosmos, trillions of years from now, every other galaxy will have receded beyond our cosmic horizon. The night sky for our distant descendants will be a lonely place, containing only the stars of our own merged supergalaxy. The evidence that other galaxies ever existed will be all but erased. The universe will appear empty, our confinement complete and absolute. This is not a failure of imagination or a limit of technology. It is a fundamental feature of our reality. We are prisoners of cosmology. The grandest dream of exploration, the voyage to another galaxy, is not just difficult or improbable. It is foreclosed by the very nature of the universe we inhabit. So, where does that leave us? Does this cosmic verdict condemn us to a future of stagnation and despair? Absolutely not. It simply redefines the scale of our destiny. To be trapped in the Milky Way is like a microbe being trapped in the Pacific Ocean. Our confinement is a palace of unimaginable size and wonder. Our home galaxy contains up to 400 billion stars. It is now believed that, on average, every star hosts at least one planet. That is hundreds of billions of worlds in our galaxy alone. Billions of gas giants, billions of rocky super-Earths, and potentially billions of planets like our own, orbiting in the habitable zones of their stars. We have barely begun to explore our own solar system. The journey to Mars remains a monumental challenge. Reaching the moons of Jupiter and Saturn will be the work of centuries. A crewed mission to the nearest star system, Proxima Centauri, 4 light-years away, would be an endeavour that would make the Apollo program look like a triviality. Our future is not one of conquering the void between galaxies, but of exploring the infinite variety and complexity within our own. It is a destiny of turning our gaze inward, to the myriad suns and worlds that make up our own stellar city. We can spend eons charting the spiral arms, exploring nebulae where new stars are being born, witnessing the final beautiful death throes of ancient suns. We can search for life, for other intelligences, on the shores of alien worlds orbiting alien stars, right here in our cosmic home. The realization that we can never leave the Milky Way should not be a cause for sorrow. It should be a source of profound humility and a catalyst for a deeper appreciation of where we are. It forces us to recognize that our galaxy is not a stepping stone. It is the destination. It is the entire stage upon which the multi-billion-year drama of humanity will unfold. Our story is not written across the universe. It is written here, among these stars, in this magnificent, swirling spiral of light. Our greatest adventures are not millions of light-years away. They are waiting for us in our own backyard. Our prison is a paradise, and we have only just begun to explore it. What if the greatest, most transformative event in the future of our world is not something we will create, but something that is already falling down upon us from the depths of time and space? There is a storm gathering on the cosmic horizon, a silent, inexorable tempest whose first winds began to blow before our planet was even born. It is a cataclysm of such unimaginable scale that it will one day rewrite the very sky above our heads, and its approach is the best-kept secret of the night, hidden in plain sight, disguised as a faint and distant smudge of light. This isn't a prediction or a possibility. It is a gravitational certainty, a celestial appointment our galaxy is destined to keep, and the journey to understand it begins not by looking out at the heavens, but by first understanding our own fragile place within them, our tiny precious island in an infinite and sometimes violent cosmic ocean. Your journey starts here. On a world of blue water and white clouds circling a very ordinary middle-aged star in a quiet suburban spiral arm of a galaxy we call the Milky Way, we feel so permanent, so stable, anchored in the familiar rhythms of day and night, season after season. But pull back, rise above the atmosphere past the silent vigil of our satellites beyond the moon's lonely orbit. Watch as the Earth shrinks to a bright marble, a single, brilliant point of light, indistinguishable from the other planets in our sun's gravitational embrace. From this vantage point, our sun is no longer a unique life-giving furnace. It becomes just one star among many a single flickering candle in a city of billions. We are already adrift. Let us travel further past the frozen frontiers of our own solar system, beyond the wandering comets of the Oort cloud, that ghostly shell of ice and rock marking the final outpost of our sun's domain. Here the silence is absolute, the distance is staggering. Light itself, the fastest thing in the universe, takes years to cross these gulfs. Our nearest stellar neighbour, the Proxima Centauri system, is a lonely lantern more than 4 light-years away, a journey that would take our fastest probes tens of thousands of years. Yet this is merely the space between doorsteps in our galactic neighbourhood. We are still nestled deep within the Orion Arm, a minor spur of gas and dust, flowing in the grand, sweeping architecture of our home galaxy. Around us drifts the raw material of creation and the ghostly relics of destruction. We pass through shimmering curtains of incandescent gas stellar nurseries, like the Great Orion Nebula, where gravitational eddies are right now crushing clouds of hydrogen into the next generation of suns. Their brilliant blue-white light illuminates the surrounding dust, a celestial canvas of breathtaking beauty. In other directions, we see the dying embers of stars like our own planetary nebulae, that are the beautiful, intricate death shrouds of suns that have exhausted their fuel, leaving behind the impossibly dense corpse of a white dwarf at their heart. Every point of light has a story, a life cycle, a history measured not in years, but in eons. This local stream of stars, this river of suns we call home, is itself, in motion, part of a colossal spinning pinwheel of 200 to 400 billion stars. To truly grasp our situation, we must leave our provincial arm behind. Our perspective must expand. We accelerate, moving now at the speed of thought, crossing thousands of light-years in a single moment. The familiar constellations of our sky dissolve into a chaotic 3-dimensional field of stars. We sweep inwards towards the galaxy's radiant, tumultuous heart. The stellar density increases exponentially. Here the night sky would have no darkness, only a continuous blazing tapestry of neighbouring suns, a perpetual twilight cast by 1,000,000 stars closer than our own Proxima Centauri. The quiet suburbs are far behind us. We have arrived in the galactic metropolis. The centre is a brilliant elongated bar of ancient golden stars, a gravitational anchor around which the entire spiral structure rotates, and at the very core, shrouded in impenetrable veils of dust and gas, lies the monster in the dark. Sagittarius A, our supermassive black hole. A gravitational singularity 4 million times the mass of our Sun, a point of infinite density from which not even light can escape. It is the silent, invisible engine of our galaxy, its immense gravity orchestrating the majestic, slow-motion ballet of billions of suns, including our own, which completes one galactic orbit every 230 million years. This is the Milky Way, our home. A vast, sprawling, breathtakingly complex island universe. For most of human history, we believed it was the only universe, a magnificent solitary kingdom of stars, but it is not solitary at all. Now we must take the most profound journey of all. We must leave our home behind entirely. We push outwards, perpendicular to the galactic plane, watching as the brilliant spiral with its glowing core and graceful arms shrinks below us. The structure becomes clear, a celestial hurricane of light and dust 100,000 light-years across. Then it too begins to diminish, joining the countless other points of light that populate the darkness. We have entered intergalactic space, the void, The scale here is almost beyond the power of language to describe. The emptiness is more complete than anything we can engineer on Earth. The silence is eternal. For thousands upon thousands of light years there is almost nothing. Just the whisper of the cosmic background radiation, the faint afterglow of the Big Bang, and the occasional lonely rogue star flung out from its home galaxy by some ancient gravitational disruption. Our own magnificent Milky Way is now just a faint luminous trail in the distance, a lonely ship on a black ocean. It is here in this profound and humbling emptiness that you can begin to see it. At first, it's a barely perceptible smudge, a phantom in the starlight that you might mistake for a flaw in your vision. For centuries, ancient astronomers catalogued it as a nebula, a little cloud nestled within our own galaxy. The Persian astronomer Abd al-Rahman al-Sufi described it in the 10th century as a nebulous smear. For 1,000 years, that is all it was, a celestial curiosity. But as our telescopes grew more powerful, the smudge began to resolve. It was not a cloud of gas within our own cosmic city. It was another city entirely, distant, separate, and immense. This is the Great Andromeda Galaxy, Messier 31, our closest major galactic neighbour, and it is a titan. As we drift closer, its true form and scale are revealed a spectacle of overwhelming grandeur. It is the big sister to our Milky Way, larger, more massive, and more luminous. Where we have perhaps 400 billion stars, Andromeda contains 1 trillion. Its spiral arms are more tightly wound, its central bulge more prominent and brilliant, glowing with the light of ancient yellowed stars. A vast shimmering disk, 220,000 light-years in diameter, it hangs in the intergalactic void like a celestial jewel. We can see its own retinue of satellite galaxies, dwarf systems, gravitationally bound to it, orbiting the colossal spiral like moths around a cosmic flame. The Triangulum Galaxy, a beautiful spiral in its own right, is also a distant companion caught in the same gravitational web. Through our virtual telescopes, we can resolve individual features within Andromeda bright blue regions, signalling intense star formation, intricate dark lanes of interstellar dust, tracing the spiral structure with exquisite detail, and a mysterious double nucleus at its core suggesting a history of ancient galactic mergers. It is by any measure one of the most magnificent objects in the known universe, a stunning, serene portrait of cosmic order and beauty separated from us by 2.5 million light-years of cold empty space. 2.5 million light-years. That's a distance so vast that the light we are seeing from it tonight began its journey when our earliest human ancestors were first walking the plains of Africa. It is a postcard from the deep past. But this serene portrait is a lie. It is the most profound illusion in the night sky. Andromeda is not a static, distant painting. It is not our neighbour peacefully keeping its distance. It is a projectile. It is an incoming cataclysm, and it is aimed directly at us. This terrifying realization was not a sudden discovery, but a dawning horror that unfolded over decades of painstaking observation. It began with an astronomer named Vesto Slipher in 1912. While studying the light from what were then called spiral nebulae, he used a spectroscope, an instrument that splits light into its constituent colours like a prism. He was searching for a chemical fingerprint, but he found something else, something deeply strange. Nearly every galaxy he observed showed what is called a redshift. The light was shifted towards the red end of the spectrum, a phenomenon caused by the Doppler effect. Just as the pitch of an ambulance siren drops as it speeds away from you, the wavelength of light from a receding object stretches, becoming redder. This redshift was the first clue that the universe was expanding, that all other galaxies were rushing away from us. All that is except for a few nearby ones. And the most prominent, the most glaring exception was Andromeda. Its light was not red. It was blue. Its light waves were not stretched but compressed, squeezed into shorter wavelengths, shifted to the blue end of the spectrum. The ambulance was not driving away. The siren was rising in pitch. Andromeda was coming towards us. Slipher's initial measurements were astounding. He calculated a velocity of 300 kilometers per second. Think about that speed. It is over 1 million kilometers per hour, a speed that could circle the Earth in less than 3 minutes. A cosmic bullet fired from the darkness. For decades, this fact remained a piece of astronomical trivia, a curious anomaly. While its radial velocity, its speed directly towards us, was known, its sideways or tangential motion was not. It was possible astronomers hoped that Andromeda would deliver a glancing blow, or perhaps miss us entirely, its trajectory taking it past our galaxy in a near-miss encounter. It took the unparalleled precision of the Hubble Space Telescope observing Andromeda over a period of 7 years to finally settle the question. By meticulously tracking the tiny, almost imperceptible sideways drift of its stars against the backdrop of far more distant galaxies, astronomers could at last calculate its true path through space. The results, when they were finally confirmed, were unambiguous. There would be no near miss, there would be no glancing blow. The faint sideways motion is negligible. Andromeda is on a direct head-on collision course with the Milky Way. The ghost in the starlight is not just an illusion, it is a predator, and we are in its sights. The great cosmic crash is not a possibility. It is our locked-in, unavoidable destiny. This is the paradox of our cosmic condition. We live our ephemeral lives on a planet in a solar system in a galaxy, whose long-term fate was sealed by gravitational forces set in motion billions of years ago, long before we ever existed. The two galaxies, our Milky Way and Andromeda, are the two most massive members of what we call the local group, a small cluster of over 50 galaxies, and in this cosmic neighbourhood, gravity, not the expansion of the universe, is the dominant force. We are gravitationally bound. We have been falling towards each other since the dawn of time. The 2.5 million light-years that separate us is not a static buffer. It is a distance that is shrinking with every passing second. Every day, Andromeda is over 26 million kilometres closer than it was the day before. The Great Collision is already underway, a slow-motion catastrophe, unfolding on a timescale that dwarfs human comprehension. In approximately 4.5 billion years, the first real effects of this encounter will begin. The outer halos of the galaxies will start to intermingle, a ghostly caress before the main event. Stars' gas and dark matter will feel the tidal pull of the approaching Leviathan. The night sky of any future inhabitants of Earth will be transformed. Andromeda will no longer be a faint, fuzzy patch. It will grow to fill the heavens, a second rival Milky Way, a spectacular, terrifying ribbon of 1 trillion suns stretching from horizon to horizon. Then the dance will begin. A gravitational contest on a scale that defies imagination, a process of destruction and chaotic rebirth that will last for hundreds of millions of years. This is not an explosion in the conventional sense. The space between stars is so vast that direct stellar collisions will be exceptionally rare. Instead, this will be a war of gravity. Entire constellations will be ripped apart. Stars our own sun, perhaps among them, will be torn from their orbits and flung into the blackness of intergalactic space, exiled forever from their home galaxy. Great streams of gas and dust will be compressed, triggering a firestorm of starbirth, a galaxy-wide baby boom that will set the merging systems alight with the brilliant, fierce glare of millions of new blue supergiant stars. The supermassive black holes at the hearts of both galaxies will be drawn inexorably towards each other, performing a final deadly orbital waltz, before merging into a single, even more massive monster, unleashing a blast of gravitational waves that will ripple across the cosmos. When the chaos finally subsides, after 1 billion years of gravitational reorganization, a new entity will be born. A giant elliptical galaxy bearing little resemblance to the two beautiful spirals that created it. Some astronomers have already given it a name, Milkomeda. A new home forged in the crucible of a galactic collision. This is the future. Written not in scripture or prophecy, but in the fundamental laws of physics, it raises the most profound questions we can ask about our own existence. What does it mean for us, a species whose entire recorded history is but a fleeting moment, to be aware of a destiny so far beyond our own timescale? Does this cosmic inevitability render our own struggles, our triumphs and failures, meaningless in the grand scheme of things? Or does this knowledge give us a new, deeper perspective, a chance to understand that we are part of a story far older and far grander than we ever imagined? The story of the Andromeda collision is not just about the death of two galaxies. It is about the nature of time, the power of gravity, and the relentless cycle of cosmic creation and destruction. And as we seek to understand the intricate details of this inevitable crash, we are forced to confront our own place in this magnificent and sometimes terrifying universe. We must now look closer at the forces at play to understand exactly how this cosmic ballet will unfold, and to ask the ultimate question, could anything including our own sun and its tiny blue planet possibly survive? Have you ever felt truly alone? That profound, heart-sinking feeling of being a solitary point of consciousness in a vast, indifferent world. It is a feeling we have all known a fundamental part of the human condition. But what if we were to tell you that this feeling is a grand illusion, that you are in fact never alone because you are a passenger on a colossal spinning vessel of rock and metal, which itself is just one traveller in a swirling luminous city of 400 billion suns? This is our home, our galaxy, the Milky Way. From our vantage point nestled here on this quiet terrestrial world, we see it not as the magnificent structure it is, but as a faint ethereal band of light splashed across the night sky, a celestial river that has captivated poets and philosophers for millennia. It is a sight of serene, almost deceptive beauty. For what we are witnessing is the cross-section of a cosmic metropolis, a sprawling barred spiral galaxy, 100,000 light-years across. Its structure is a masterpiece of gravitational architecture, an intricate dance of matter and energy on a scale that defies our intuition. Imagine it a brilliant incandescent core, a dense sphere of ancient stars packed so tightly that from a world inside the night would never truly fall. At its very heart lurks a monster of unimaginable power, Sagittarius A, a supermassive black hole 4 million times the mass of our Sun. It is the galaxy's gravitational anchor, the silent conductor of this immense celestial orchestra, its presence felt in the precise sweeping arcs of every star caught in its sway. Extending from this blazing centre are the great spiral arms, the vibrant star-forming suburbs of our galactic city. They are not solid structures, but rather cosmic traffic jams, density waves of gas and dust moving slowly through the galactic disk. As interstellar clouds drift into these arms, they are compressed, squeezed by gravity until they collapse and ignite, giving birth to dazzling new generations of stars. These arms the Perseus, arm the Scutum Centaurus, arm the Norma arm are awash in the brilliant blue light of young hot suns and painted with the rosy glow of nebulae, the stellar nurseries where creation is a constant ongoing spectacle of fire and light. Our own sun does not live in these glittering chaotic downtown districts. Instead, we find ourselves in a far more tranquil, almost pastoral location. We reside within a minor spur of one of the great arms, the Orion Cygnus arm, about 27,000 light-years from the galactic core. Here in the galactic suburbs, the stellar traffic is lighter, the neighbourhood quieter. It is a position that has likely been crucial for the development of life on Earth, shielding us from the intense radiation of the galactic centre and the disruptive gravitational tides of the more crowded spiral arms. We live in a calm harbour orbiting the galactic centre at a breathtaking 500,000 miles per hour, completing one full galactic year every 230 million Earth years. The last time our solar system was in this position, dinosaurs were just beginning their reign. This, the disk of our galaxy, is where most of the familiar action happens, but it is not the full story. Surrounding this entire flattened structure like a vast ghostly sphere is the galactic halo. It is a realm of ancient scattered stars and enormous mysterious globular clusters, spherical swarms of hundreds of thousands of the galaxy's firstborn suns locked in tight gravitational embraces orbiting the Milky Way like ancient satellites. And permeating this halo extending far out into the intergalactic void is an even greater mystery, a colossal invisible sphere of dark matter. We cannot see it, we cannot touch it. Yet its gravitational influence is what holds our galaxy together, preventing our rapidly spinning disk from flying apart into the cosmic darkness. It is the unseen scaffolding upon which our luminous home is built. This is our address in the cosmos, a small rocky planet orbiting an average star in a quiet suburban arm of a vast spiral city of stars, which is itself embedded in an even vaster invisible halo of mysterious matter. For most of human history, we believed this cosmic city was all there was. The Milky Way was not a galaxy. It was the universe. The stars we saw, the nebulae we charted, they were all believed to be local residents. fellow citizens of our singular magnificent island of light. Beyond its misty shores there was only an endless eternal empty ocean of night. This was the accepted map of creation, a model of comfortable if solitary grandeur. But for centuries a single stubborn smudge of light in the autumn sky refused to fit neatly into this picture. A faint oval-shaped phantom that whispered of a universe far stranger and more expansive than anyone had ever dared to imagine. It was first formally documented not by a European with a telescope but by the Persian astronomer Abd al-Rahman al-Sufi in the year 964. In his Book of Fixed Stars, he described it with beautiful simplicity as a small cloud. For nearly 1,000 years it remained just that, a curiosity, a celestial wisp. When early telescopes were pointed toward it, the mystery only deepened. In 1612, the German astronomer Simon Marius observed it, describing its light as being like that of a candle shining through horn. It was not a sharp, distinct point of light like a star, nor did it seem to resolve into a glittering collection of stars like a globular cluster. It was something else. When the French comet hunter Charles Messier catalogued it in 1764 to prevent confusing it with an actual comet, he designated it Messier 31. He, like everyone else, labelled it a nebula, the Latin word for cloud or fog. It became one of many such spiral-shaped nebulae that astronomers were discovering ethereal celestial pinwheels scattered across the sky. But what were they? Were they swirling clouds of gas within our own Milky Way, perhaps new solar systems in the process of formation? Or were they something far more profound? This single question would ignite one of the most important intellectual battles in the history of science, a conflict that would fundamentally redraw our map of the universe and redefine humanity's place within it. The stage for this confrontation was set in Washington, D.C., in April of 1920 at the Smithsonian Museum of Natural History. The event was billed as the Great Debate, and the two intellectual gladiators were two of the most respected astronomers of their time, Harlow Shapley and Heber Curtis. At stake was nothing less than the true scale of existence. In one corner stood Harlow Shapley, a brilliant, ambitious and supremely confident astronomer from the prestigious Mount Wilson Observatory. Shapley was the champion of the big galaxy model. He had recently completed groundbreaking work using a special type of star, a Cepheid variable, to measure the true size of the Milky Way for the first time. His results were staggering, suggesting our galaxy was a colossal 300,000 light-years, across 10 times larger than anyone had previously believed. In Shapley's view, this gargantuan structure was the entirety of the universe. There was simply no room for anything else. The spiral nebulae, including that faint patch in the constellation Andromeda, must therefore be local phenomena, relatively small gas clouds inside our own galactic borders. Shapley presented compelling evidence. He pointed to observations of a nova, an exploding star that had briefly flared up within the Andromeda Nebula. If Andromeda were as far away as his opponent claimed, he argued, this single exploding star would have had to outshine an entire galaxy, an energetic output so preposterous it bordered on the absurd. Furthermore, another astronomer had claimed to have measured the rotation of a spiral nebula, finding that its edges were moving at incredible speeds. If these objects were truly as massive and distant as proposed, their outer edges would be moving faster than the speed of light, a physical impossibility. Shapley's case was powerful, built on his own revolutionary research, and it painted a picture of a single, majestic, all-encompassing galaxy. We lived in the universe, and the universe was us. In the other corner stood Heber Curtis, an older, more reserved astronomer from the Lick Observatory. Curtis was the lonely proponent of a radical, almost fantastical idea, first proposed by the philosopher Immanuel Kant. He argued that the spiral nebulae were not local clouds at all. They were, he proposed, island universes, vast independent galaxies just like our own Milky Way, drifting in the cosmic void at unimaginable distances. Our galaxy was not the whole universe, but merely one island in a vast cosmic archipelago. Curtis's evidence was more subtle, more interpretive. He pointed out that the spectra of these spiral nebulae showed a massive Doppler shift, a stretching of their light toward the red end of the spectrum, which suggested they were moving away from us at tremendous velocities, far faster than any object known within the Milky Way. Why would these clouds be fleeing from us with such urgency? If they were our neighbours, he also highlighted the discovery of far more novae within Andromeda than in any other part of our sky, suggesting it was a place of immense stellar activity, consistent with an entire galaxy's population of stars, and most persuasively he showed photographs of other spiral nebulae seen edge-on. They revealed a distinct dark lane of dust bisecting their bright centres, a feature that looked uncannily similar to the band of dust we see when we look at the plane of our own Milky Way. It was as if we were looking at our own home in miniature from a vast distance. For 2 days they debated, presenting their conflicting data, their rival interpretations. Shapley argued from a position of authority, his work having just redefined our own galaxy. Curtis argued from a position of pattern recognition of cosmic perspective. The scientific community was divided. The debate ended in a stalemate. Both men were right about some things and wrong about others. Shapley was correct that his galaxy was huge, though he had overestimated its size. Curtis was correct about the island universes, though his estimate for the Milky Way's size was too small. The truth lay somewhere in between, and the universe was both bigger and more populated than either of them could conclusively prove. The question remained unanswered, hanging in the air. The final decisive evidence would not come from debate or theory, but from a single man working night after solitary night high atop a mountain in California, peering into the heavens with a new giant eye. The man was Edwin Hubble. The eye was the new 100-inch Hooker telescope at Mount Wilson, the most powerful telescope on Earth. It was a technological marvel, a light-gathering machine capable of resolving the universe's secrets with unprecedented clarity. Hubble dedicated himself to solving the mystery of the spiral nebulae, focusing his immense patience and the telescope's immense power on that persistent smudge known as Messier 31. He began taking a series of long-exposure photographs capturing the faint ancient light from the nebula onto delicate glass plates. Night after night he would guide the telescope, collecting photons that had travelled for an unknown eternity to reach his mountaintop observatory. His goal was simple: to find definitive proof one way or another. He was looking for stars, individual points of light within the nebula that could finally settle the question of its nature and its distance. And then, on the night of October 5th, 1923, he found it. On a photographic plate of the Andromeda Nebula's outer regions, he identified a single peculiar star. Comparing it to photos from previous nights, he realized it was not constant. It was blinking, pulsing with a steady rhythmic beat. He had found a Cepheid variable star. This was the key, the cosmic Rosetta Stone. As Harlow Shapley himself had pioneered, Cepheid variables are a type of cosmic yardstick. There is a direct, unwavering relationship between the period of their pulse, how long it takes them to brighten and dim, and their true intrinsic luminosity. They are standard candles. By measuring the period of the star's pulse, Hubble could calculate how bright it truly was. And by comparing that true brightness to how dim it appeared on his photographic plate, he could calculate its distance with astonishing precision. It is the same principle you use to judge the distance of a car's headlights on a dark road. The dimmer they appear, the farther away they must be. Hubble performed the calculations. He checked them again, and then again. The number that emerged was not just large, it was revolutionary. It was world-view shattering. His Cepheid variable star, and by extension, the nebula it resided in, was located at a distance of nearly 1 million light-years from Earth. At the time, even Shapley's most generous overestimated model of the Milky Way placed its edge at only 300,000 light-years. This blinking star was more than 3 times farther away than the edge of our own galaxy. It could not possibly be a local cloud. It was an impossible distance for a mere gas cloud to be. The implications were immediate and profound. Heber Curtis had been right. Immanuel Kant had been right. That faint, misty patch of light was not a neighbour. It was another city of stars and island universe, as vast, as majestic, and perhaps even larger than our own Milky Way. In a single moment, with a single calculation, our universe was broken open. It was no longer a solitary island of light in an infinite void. It was a cosmos teeming with such islands, countless galaxies stretching out in every direction, as far as his great telescope could see. Humanity's place in the universe was forever changed. We were not the centre of everything, We were citizens of one metropolis among an uncounted number of others. The great debate was over. The small cloud, the spiral nebula Messier 31, was finally given its proper name and status. It was the Andromeda Galaxy. Our closest major galactic neighbour, our cosmic twin. The resolution of this profound mystery, the discovery of our true place in the cosmos, should have been a moment of pure intellectual triumph, a time of quiet satisfaction. But as astronomers began to study this newly discovered sibling galaxy with ever greater scrutiny, a new, more unsettling mystery began to emerge from the data. When we studied the light from nearly every other distant galaxy, we saw that it was stretched, redshifted, a clear sign that they were all rushing away from us, carried outward by the expansion of the universe itself. But Andromeda's light was different. It was not stretched toward the red. It was compressed. It was blue-shifted. And that could only mean one thing. Alone among the billions of galaxies in the cosmos, this one was not moving away. It was coming right for us. But this incredible, terrifying premonition begs a profound question. How could we possibly know? How can we, from our tiny vantage point on a pale blue dot, condemn two of the cosmos's most magnificent creations to a fate billions of years in the future? The story of this prophecy is not one of ancient myths or divine revelation. It is a story of human ingenuity, of relentless curiosity. It is a detective story written in the language of starlight, a case built over a century clue by painstaking clue. To begin, we must travel back in time to an era when our cosmic address was far smaller, and the universe itself felt profoundly more constrained. In the early 20th century, Andromeda was not a sister galaxy. It was the Great Andromeda Nebula, a mysterious ethereal smudge in the constellation of the same name. For centuries, astronomers debated its true nature. Was it a swirling cloud of gas within our own Milky Way, a stellar nursery giving birth to new suns nearby? Or was it something far more profound, an entire island universe, a galaxy like our own lying at a truly incomprehensible distance? The question hung in the air, a fundamental barrier to our understanding of the cosmos. Without knowing its distance, Andromeda remained a ghost, its true scale and identity shrouded in cosmic fog. The man who would pierce that fog was Edwin Hubble. Perched high atop Mount Wilson in California, he commanded the most powerful instrument on Earth, the colossal 100-inch Hooker telescope. It was a technological marvel, a gateway to the heavens that could gather light from objects fainter and farther than ever before. Hubble's mission was to solve the riddle of the spiral nebulae. Night after night he guided the telescope, capturing their faint ancient light on fragile glass photographic plates. He was searching for a very specific type of clue, a key that could unlock the problem of cosmic distance. He was looking for a very special kind of star. They are called Cepheid variables, and they are the unsung heroes of modern cosmology. These stars are not content to shine with a steady glow. Instead, they live in a perpetual state of flux, rhythmically brightening and dimming with a pulse as reliable as a celestial heartbeat. In 1908, a brilliant astronomer named Henrietta Swan Leavitt, working tirelessly at the Harvard College Observatory, made a discovery that would forever change our place in the universe. While studying thousands of these pulsing stars in a nearby dwarf galaxy, she noticed a startling, unequivocal relationship. The brightest Cepheids had the longest periods. They took more time to pulse. Dimmer ones beat more quickly. The implication was electrifying. If you could measure the rhythm of a Cepheid's pulse, its period, you could know its true intrinsic brightness, how much light it was actually putting out. They were in effect cosmic lighthouses of a known wattage. They are what astronomers call a standard candle. Imagine you see a candle in the dark. If you know it's a standard 100-watt light bulb, you can tell exactly how far away it is just by measuring how dim it appears to you. A faint glimmer means it's far away. A brilliant glow means it's close. Henrietta Leavitt had handed astronomers the universe's own yardstick. Now all Edwin Hubble had to do was find one in Andromeda. The task was monumental, like trying to spot a single firefly, flickering in a city seen from across an entire continent. For months he meticulously photographed the Andromeda's nebula, comparing plates, searching for the telltale flicker of a single star. Then, on the night of October the 6th, 1923, it happened. Examining a photographic plate labelled H335H, Hubble identified a tiny pinprick of light that was not present on earlier images. He initially marked it with an N for nova, a type of exploding star, but as he compared it with other plates, he saw that this star was different. It appeared vanished and reappeared. It was pulsing. In a moment of heart-stopping revelation, he crossed out the N and scrawled in bold red letters VAR for variable. He had found his Cepheid. The universe was about to crack wide open. Hubble carefully measured the star's rhythm, the period of its pulse. Using Leavitt's law, he calculated its true intrinsic luminosity. Then he measured its apparent brightness as seen from Earth, a mere phantom glimmer on his photographic plate. The final calculation was both simple and world-shattering. For this star to appear so faint yet be so intrinsically bright, it had to be located at a distance of nearly 1 million light-years. That was an order of magnitude farther than anyone had ever measured, far, far outside the most generous estimates for the size of our Milky Way. In that single moment, Andromeda the nebula died, and Andromeda the Galaxy was born. It was an island universe, a sprawling city of stars as large if not larger than our own. And with that one discovery, our universe expanded from a single galaxy into a vast majestic cosmos teeming with them. Hubble had found the first crucial piece of evidence in our cosmic investigation. He had established the scene of the crime. He knew where Andromeda was. But the most pressing question remained unanswered. Where was it going? The answer to that question had remarkably already been uncovered years before Hubble's great discovery by a quiet, unassuming astronomer from rural Indiana named Vesto Slipher. Working at the Lowell Observatory in Arizona, Slipher was a master of one of astronomy's most powerful and subtle tools, spectroscopy. If a telescope is an astronomer's eye, a spectroscope is their decoder ring. When you pass light through a prism, it splits into its constituent colours, a rainbow. A spectroscope does the same for starlight, but with far greater precision. And when you examine the spectrum of a star or a galaxy, you see more than just a smooth continuum of colour. You see a series of fine dark lines interrupting the rainbow. These lines are a cosmic fingerprint, a celestial barcode. Each dark line represents a specific wavelength of light that has been absorbed by a particular chemical element in the star's atmosphere: hydrogen, helium, calcium ion. The pattern of these lines tells you exactly what a distant object is made of, but it can tell you something even more profound. It can tell you how it's moving. This phenomenon is woven into the fabric of our everyday experience. You know it as the sound of a passing ambulance. As the siren races towards you, the sound waves are compressed, their frequency increases, and you hear a higher-pitched wail. As it speeds away, the sound waves are stretched out, their frequency drops, and the pitch falls lower. This is the Doppler effect. Light, being a wave, behaves in precisely the same way. If a galaxy is moving away from us, the light waves it emits are stretched. This stretching shifts their colour towards the red end of the spectrum. Astronomers call this a red shift. If a galaxy is hurtling towards us, its light waves are compressed. They are squeezed to a higher frequency, shifting its light towards the blue end of the spectrum. A blue shift. The cosmic fingerprint of spectral lines moves along with the light. By measuring the exact position of these known elemental lines and comparing them to where they should be, we can measure a galaxy's motion towards or away from us with incredible precision. Beginning in 1912, Vesto Slipher began the painstaking work of capturing the spectrum of the Andromeda Nebula. The light was so faint that a single observation required an exposure lasting 20, 30, even 40 hours spread over multiple nights. At the time, most astronomers assumed the nebulae were chaotic systems with random motions. Slipher found that most of them were in fact redshifted, a key clue that would later lead Hubble to discover the expansion of the universe. But when Slipher finally developed and analysed his plate of Andromeda, he saw something that must have made his heart pound. The spectral lines, the unmistakable fingerprints of its stars, were not shifted to the red. They were dramatically, unambiguously shifted to the blue. His calculations revealed a speed that was simply stunning. The Andromeda Nebula was rushing towards our solar system at a blistering 300 kilometers per second. That's over 1 million kilometers per hour. It was a result so strange, so completely at odds with the general trend of other nebulae that it stood out as a profound cosmic anomaly. At the time, no one knew what to make of it. Without knowing Andromeda's distance, the speed was just a number, a piece of data without context. But when Hubble's discovery of its true distance finally came a decade later, the two puzzle pieces locked into place with chilling clarity. Slipher's blue shift was the smoking gun. The great island universe, our nearest galactic neighbour, was not just a passive spectator in the cosmic ballet. It was an active participant, and it was on a direct collision course with us. The case was building, the evidence mounting. We had a location, and we had a direction of travel. But this was not yet conviction. There was still a chance, a glimmer of hope for a near miss. You see, Slipher's measurement of the blue shift could only reveal one component of Andromeda's motion: its radial velocity. That is the speed directly along our line of sight. It couldn't tell us anything about its transverse velocity, its sideways motion across the sky. Think of it like this: a distant train might be heading towards your town, but if it's on a parallel track, it will miss you completely. To an observer looking straight down the line, it would appear to be coming directly at them until the very last moment. For Andromeda to miss us, it would need a significant sideways velocity enough to carry it clear of the Milky Way's gravitational grasp. For decades, measuring this sideways drift was considered impossible. The galaxy is so far away that any such motion would be infinitesimally small from our perspective on Earth. It would be like trying to measure the speed of a single human hair growing as seen from the other side of a continent. Our ground-based telescopes, their view blurred and distorted by our own restless atmosphere, stood no chance. The final piece of evidence, the one that would seal our galaxy's fate, would have to wait for a new era of astronomy. It would have to wait for us to leave the ground behind. The definitive proof arrived thanks to two of the most ambitious and sophisticated observatories ever built: the Hubble Space Telescope and the European Space Agency's Gaia mission. Floating high above the obscuring veil of Earth's atmosphere, the Hubble telescope has a vision of unshakable clarity. Over the course of more than a decade, astronomers used Hubble to conduct one of the most patient observational campaigns in history. They repeatedly imaged select regions of the Andromeda Galaxy, meticulously tracking the positions of thousands of its individual stars. The goal was to measure their almost imperceptible sideways drift against the backdrop of even more distant, effectively stationary galaxies. It was a measurement of breathtaking precision, a cosmic survey on a scale previously unimaginable. At the same time, the Gaia spacecraft was undertaking an even grander project to create the most precise three-dimensional map of our own galaxy ever conceived. By charting the positions and motions of over 1 billion stars in the Milky Way, Gaia has given us an unprecedented understanding of our own home, including the precise motion of our Sun as it orbits the galactic centre. To know where you're going, you must first know how you yourself are moving. When the data from both missions were finally combined, the astronomical community held its collective breath. The Hubble data provided Andromeda's sideways motion. The Gaia data provided the Milky Way's. Subtracting one from the other revealed their true relative trajectory. The result was the final nail in the coffin of uncertainty. Andromeda does have a sideways velocity, but it is small, far, far too small to allow it to escape its destiny. It will not be a glancing blow. It will not be a near miss. The refined calculations, now honed to an astonishing degree of accuracy, show that the two galaxies are destined for a near head-on collision. The case was closed. The evidence undeniable. The verdict delivered by the unblinking eyes of our most advanced instruments was guilty of inevitable collision. But this raises a final deeper question. Why? In a universe that is on the whole expanding with almost every other galaxy flying away from us, why are we and Andromeda locked in this powerful gravitational embrace? The answer lies in the greatest mystery of modern astrophysics, an invisible substance that dictates the fate of galaxies. The stars, the gas, the dust, all the luminous matter we can see in both galaxies accounts for only a fraction of their total mass. Decades ago, astronomers like Vera Rubin noticed something deeply strange about the way galaxies spin. The stars on their outer edges were moving far too quickly. Based on the gravity generated by the visible matter alone, these outlying stars should have been flung off into the void, like children flying off a merry-go-round that's spinning too fast. For them to remain in stable orbits, there had to be something else there. Something massive, something invisible, something providing the extra gravitational glue needed to hold the galaxy together. We call it dark matter. It is a vast spherical halo of unknown particles surrounding each galaxy like a ghostly gravitational cocoon. This invisible scaffolding is far larger and more massive than the luminous galaxy we see nestled within it. And it is the colossal gravitational attraction between the Milky Way's dark matter halo and Andromeda's dark matter halo that is the true engine of this collision. The stars we see are merely along for the ride. We are not just two islands of light drifting towards one another. We are two immense invisible titans of gravity, two gravitational ghosts that have been pulling each other closer across millions of light years of emptiness for billions of years. Their combined gravity has completely overwhelmed the general expansion of the universe, creating our own little pocket of cosmic collapse. This is the unseen hand guiding our galaxies to their shared destiny. And now, with the evidence secure and the physics understood, we can finally turn our gaze to the future. We can ask the ultimate question, what will it look like when these two cosmic titans finally meet? And so, the verdict is in. The cosmic jury, comprised of the unyielding laws of physics and the irrefutable evidence of light itself, has returned its judgment. The great Andromeda Galaxy is not merely a neighbour passing in the night. She is our destiny, an emissary from the distant universe bearing a message of inevitable, violent and ultimately creative union. The debate that once echoed in the halls of astronomy, the quiet uncertainty of if, has been silenced forever. A new question now dominates our forward gaze, a question of staggering scale and profound consequence, not if, but precisely when and exactly how this celestial drama will unfold. To answer that, we can no longer rely on telescopes alone to peer into the future. For this, we must build our own universes. We turn to the modern temples of computation, cathedral-like rooms filled with supercomputers that hum with a power rivaling a small city. Here in the silent, chilled air, scientists become cosmic cartographers, charting the currents of a future that has not yet come to pass. They load these digital engines with every scrap of data we possess, the mass of Andromeda, the precise velocity of its approach, the distribution of its hundreds of billions of stars, the vast shimmering clouds of interstellar gas, and most critically, the immense invisible scaffolding of dark matter that binds it all together. They do the same for our own Milky Way, creating a perfect digital twin of our home. Then with a single command they press play on the universe. The simulation begins not in real time, but in colossal leaps of millions of years per second. What we are about to witness is not fantasy. It is a forecast born from the most rigorous physics we know, a gravitational prophecy written in the language of mathematics. The machine calculates the gravitational pull of every single particle upon every other, an unimaginably complex web of interactions that will dictate the shape of everything to come. It is our only reliable window into a future so distant it strains the very limits of human comprehension. The cosmic clock inside the machine begins its inexorable countdown. 10 million years pass in a blink. 100 million. 1 billion. On Earth, continents will drift, mountains will rise and fall, and entire epochs of life will emerge and vanish into fossil records. But in the void, the two galaxies continue their patient, silent approach, still separated by an ocean of darkness. For now, the night sky, as seen from a future Earth, would look much the same. Andromeda remains a faint ghostly smudge, a promise of what's to come. 2 billion years, 3. The gap narrows, the gravitational pull between the two titans growing stronger with every passing millennium. Now the change begins to be perceptible to the naked eye. Andromeda is no longer a smudge. It is a disk, a distinct and growing spiral in the starfields. Then we arrive at the pivotal moment, the beginning of the end for the two galaxies as we know them. The simulation freezes the clock at approximately 3.75 billion years from now. At this juncture, Andromeda will have swollen in our sky to a breathtaking spectacle, a shimmering celestial island that dominates the view, its spiral arms and glowing core plainly visible. It would be a sight of terrible beauty, a source of myth and wonder for any beings who might gaze upon it. The Milky Way, from Andromeda's perspective, would be an equally magnificent sight, a luminous band of light stretching across their sky. The two galaxies are now poised on the brink like two heavyweight fighters about to engage. The space between them has shrunk to a mere stone's throw in cosmic terms. The first true interaction is not a clash, but a caress, a whisper. It is purely gravitational. Long before a single star from Andromeda enters what we consider our galaxy's territory, its immense gravity begins to make its presence felt. Imagine dropping a stone into a still pond. The ripples spread far from the point of impact. Andromeda is that stone, and the fabric of our galaxy is that pond. The outermost, most tenuous spiral arms of the Milky Way, the delicate fringes of our galactic city, are the first to feel the strain. The perfectly sculpted spiral we know today begins to warp, to bend out of shape. Stars in these outer regions, held in a delicate gravitational balance for eons, find their orbits subtly but irrevocably altered. They are being tugged, pulled by an unseen force, a cosmic tide that is only beginning to rise. This is the start of a process known to astronomers as tidal disruption. The galaxy, with the more concentrated core Andromeda, acts as the primary gravitational anchor. Our Milky Way, slightly less massive, begins to yield. Its beautiful arms, those rivers of stars and gas that have defined its shape for billions of years, are stretched and distorted. The simulation shows them being pulled forward like saltwater taffy drawn out into space towards the approaching behemoth. The result is the creation of one of the most hauntingly beautiful phenomena in the universe, a tidal tail. A vast, luminous streamer of stars, gas and dust, hundreds of thousands of light years long, is ripped from the body of the Milky Way and flung into the intergalactic void. This is not a gentle process. It is a slow, majestic and unbelievably violent act of galactic dismemberment. Millions of stars, torn from the safety of their home, are cast out into the cold, empty darkness between the galaxies, forming a shimmering bridge connecting the two. Nebulae, those stellar nurseries pregnant with the potential for new suns and new worlds, are stretched thin and torn asunder, their star-forming processes thrown into chaos. For any civilization living on a planet in this tidal tail, their sky would be a scene of unimaginable change. Their home star would no longer be part of a grand orderly spiral, but a refugee in a chaotic river of exiles, drifting ever further from the galactic core they once called home. Andromeda itself is not immune. As it pulls on us, we pull back. Its own outer arms begin to distort its own tidal tails, flaring out into the void, a mirror image of the disruption it inflicts upon us. The two galaxies are now connected by these ghostly luminous filaments of orphaned stars, two dying kingdoms reaching out for one another in a final fatal embrace. This entire overture, this gravitational dance of distortion and disfigurement, takes hundreds of millions of years to play out. It is a slow-motion catastrophe of unimaginable proportions. Then comes the main event. At roughly 4.5 billion years from today, the primary disks of the two galaxies make their first pass. Here, our human intuition for collisions fails us completely. We imagine a thunderous crash, a cosmic demolition derby of star smashing into star. But the reality revealed by the simulation is both stranger and more profound. Space even inside a galaxy is mostly space. The distance between individual stars is so mind-bogglingly vast that the number of direct head-on collisions will be statistically insignificant. Perhaps a handful of stars out of the trillions involved will actually impact one another. Instead of a solid crash, what happens is a ghostly interpenetration. The Andromeda Galaxy will pass directly through the Milky Way, like a phantom army marching through another. For a period of millions of years, the two separate realities of these galaxies will coexist, occupying the same volume of space. Stars from Andromeda will weave between the stars of the Milky Way. Our Sun, if it still exists, might find itself with new, stellar neighbours, visitors from another galaxy, passing within a few light years before continuing on their journey. The sky from Earth would be an incomprehensible storm of new stars, a celestial tapestry woven from two different cosmic threads. The familiar constellations would be lost, drowned in a sea of alien suns. But the absence of physical impacts does not mean an absence of chaos. The real violence is gravitational. Imagine two people walking through each other, but as they do, each one violently shakes and contorts the other's skeleton. This is what happens to the galaxies. As the dense cores of the two galaxies sweep past each other, they unleash gravitational shockwaves of unimaginable power. The orderly, predictable orbits of billions of stars are shattered. The gravitational gyroscope that has kept our solar system in its comfortable path for eons is broken. This is where the gravitational slingshot effect comes into play. A star's path is no longer dictated by the familiar pull of its home galaxy's centre. It is now a chaotic game of cosmic billiards, where the cue ball is the colossal gravitational field of the passing galactic core. The simulation shows stars being captured by Andromeda's gravity, their allegiance forcibly switched. It shows others being accelerated to incredible speeds and flung out of both galaxies, entirely ejected into the lonely abyss of intergalactic space, destined to wander the great darkness alone for eternity. They become hypervelocity stars, cosmic exiles. Our own solar system faces this uncertain future. The simulations cannot predict our precise fate, as a tiny change in our initial position results in a wildly different outcome billions of years later. But they give us the probabilities. There is a small but terrifying chance that we could be one of those exiles cast out into the endless night, our connection to our home galaxy severed forever. A more likely scenario is that we are thrown into a new highly eccentric and chaotic orbit, perhaps plunging us periodically towards the turbulent new galactic centre, or flinging us far out into the newly formed stellar halo. The familiar stable environment we have known for the entirety of Earth's history will be gone. The pass-through is not a single event. It is the beginning of a cycle. Gravity is a relentless force. Having passed through each other, the two galaxies do not have enough momentum to escape their mutual pull. Like a pendulum reaching the apex of its swing, they will slow stop and then begin to fall back towards each other once more. The invisible chains of dark matter that surround them ensure their fate is sealed. They are now gravitationally bound, locked in a death spiral from which there is no escape. The first pass has irrevocably broken their original structures, but the process of merging has only just begun. This right here is the true turning point in our galactic history. The moment the first pass-through is complete marks the end of the Milky Way as a distinct spiral galaxy. It also marks the end of Andromeda as we know it. Their identities have been shattered, their elegant structures ruined. They are now two wounded, distorted masses of stars, bleeding luminous tails into the void, destined to collide again and again, each pass more violent and disruptive than the last. They are no longer two separate entities on a collision course. They are now the inseparable components of a new chaotic system in the violent throes of creation. The grand and elegant spirals that graced the cosmos for more than 10 billion years have been erased from the universe. In their place is a tangled, chaotic maelstrom of stars, a battlefield strewn with the wreckage of what once was. The star-forming nebulae, once serene stellar nurseries, have been violently compressed by the gravitational shockwaves. This compression triggers a furious burst of star formation across the merging galaxies. The chaos ignites a wave of creation, a galactic fireworks display of brilliant hot blue stars that illuminate the wreckage. It is a cosmic forest fire, a destructive event that simultaneously clears the way for new growth, a violent birth amidst the ruins of the old order. What we are witnessing in these digital universes is the fundamental engine of cosmic evolution. Galaxies are not static islands. They are dynamic living entities that grow and change by consuming one another. This is how the largest galaxies in the universe, the great ellipticals, are forged through a long and brutal history of mergers and acquisitions. We are not just watching a distant abstract event. We are watching our own galaxy's metamorphosis, its final transformative chapter. The Milky Way, our home, the river of light, that has inspired wonder since the dawn of humanity, is entering the first stage of its own dissolution. But the story is far from over. This first ghost-like passage and the subsequent fall back together is merely the prelude to an even more dramatic and powerful event. Because at the heart of both galaxies a monster lies in wait. At the centre of the Milky Way resides Sagittarius S, a supermassive black hole 4 million times the mass of our Sun. At the heart of Andromeda lies an even greater beast, a black hole over 100 million solar masses. These two gravitational anchors, these singularities, that have governed their respective galaxies for eons, have survived the initial pass. And now, as their parent galaxies are drawn back together for the second, even more violent encounter, these two monsters are being set on a collision course of their own. The true cataclysm is yet to come, and so the first touch is not a clash of arms but a ghostly caress. The magnificent spiral arms of our Milky Way and the great Andromeda Galaxy, having crossed the void for 4.5 billion years, finally begin to interpenetrate, to pass through one another like two phantoms merging in the cosmic twilight. You might be bracing for impact for the thunder of a billion stellar collisions. The very word crash conjures images of fire and cataclysmic ruin. But the reality of this encounter is at once more subtle and far more profound. The truth lies in a paradox of scale that the human mind struggles to contain. Galaxies are not solid objects, they are empires of emptiness. If you were to shrink our Sun down to the size of a single grain of sand, its nearest stellar neighbour, Proxima Centauri would be another grain of sand located more than 4 miles away. The space between the stars is an abyss, a near-perfect vacuum so vast that the odds of any two stars physically colliding during this merger are infinitesimally small, less than 1 in a trillion. Imagine two immense sandstorms, each containing billions of grains drifting toward each other across a desert. As they merge, how many individual grains of sand do you think would actually hit? Almost none. They would simply pass each other by their collective shape, blurring the two storms, becoming one larger, more turbulent cloud. This is the fate of the stars. They are the silent, untouchable witnesses to a much greater drama, one orchestrated not by matter, but by the invisible hand of gravity. It is here in the unseen ocean of gravitational fields that the true battle is waged. For billions of years, every star in our galaxy has followed a predictable, graceful orbit around the galactic core, a celestial clockwork of immense precision. But now, a new master has entered the system. Andromeda's gravity, an influence equal to our own, begins to pull and twist to rewrite the ancient laws that have governed our cosmic home. The first consequence is a profound and spectacular reorganization. The elegant pinwheel structures of both galaxies, their iconic spiral arms, are doomed. These arms are not solid structures but transient density waves, traffic jams of stars and gas moving through the galactic disk. As the two gravitational fields churn together, these delicate patterns are torn asunder. Stars are wrenched from their stately processions, flung into chaotic new trajectories that loop high above and below the galactic plane. We can see this happening elsewhere in the cosmos in other galactic mergers, frozen in time by the speed of light. We see galaxies stretched into grotesque, beautiful shapes, pulling luminous tendrils of stars from one another like celestial taffy. These are tidal tales, rivers of suns torn from their homes, and cast out into the intergalactic darkness, monuments to gravity's raw power. Our own solar system will be a part of this grand chaotic ballet. The familiar constellations that have guided humanity for millennia will vanish. The night sky will become a swirling, unfamiliar tapestry as stars from our local neighbourhood are scattered across tens of thousands of light years. This is not destruction. It is a violent cosmic rebirth. This gravitational chaos, this churning of two galactic titans, serves as the universe's most powerful trigger for creation. While the stars themselves glide past one another untouched, the same cannot be said for the vast diffuse clouds of gas and dust that drift in the interstellar medium. These are the stellar nurseries, the cold, dark reservoirs of raw material from which new suns are born. For eons, these clouds have existed in a delicate equilibrium, their own feeble gravity only just balanced against their internal pressure. But as the two galaxies merge, immense shock waves of gravitational compression begin to ripple through this placid medium. It is like clapping your hands in a room full of dust motes. The clouds are slammed together, squeezed and destabilized on an unimaginable scale. Across tens of thousands of light years, countless pockets of gas are suddenly pushed past their breaking point, the critical density at which their own gravity can take over and trigger a runaway collapse. and with that collapse comes ignition. A firestorm of star formation erupts throughout the merging galaxies. Regions that once birthed maybe 1 or 2 new stars every million years are suddenly ablaze, forging thousands of them in a furious incandescent burst. Astronomers call these starburst regions, and they are among the most luminous and spectacular phenomena in the entire universe. From our distant future vantage point, we would see our merging home lit up with brilliant sapphire blue knots of light. These are the new stellar nurseries glowing with a fierce energetic radiation of tens of thousands of newborn massive stars. These giant blue stars burn 1,000 times brighter than our sun, but they live fast and die young, exhausting their nuclear fuel in a few million years before exploding as brilliant supernovae. Their violent deaths will seed the new galaxy with heavy elements, the carbon, oxygen and iron that will form the next generation of planets, and perhaps the next generation of life. The merger, a force of apparent chaos, becomes the universe's ultimate act of renewal. It is a cosmic forest fire, clearing out the old to make way for the new, triggering a wave of creation that will define our galaxy for 1 billion years to come. But this grand spectacle raises a deeply personal question. Amidst this celestial tempest, this gravitational maelstrom where entire star systems are relocated and cosmic landscapes are redrawn, what becomes of us? What is the fate of our small yellow sun and its fragile retinue of planets? Here, the laws of probability and physics offer a surprising reassurance. While our solar system is almost certain to be evicted from its current home, ripped from the familiar Orion arm, and thrown onto a completely new path, the chances of it being destroyed are vanishingly small. The Sun, along with its planets, is a tightly bound gravitational system. The pull of Jupiter on the Earth is immensely stronger than the distant diffuse pull of a passing star hundreds of thousands of times farther away. Even as we are flung through the churning heart of the merger, our local planetary family will hold together. Our new home will be a different one, a new cosmic address. Computer simulations running the gravitational dance of billions of stars forward in time show that our Sun will most likely be cast into a much wider, more eccentric orbit within the new, larger galaxy that is forming. We could be thrown into the galactic halo, a vast spherical region of older stars that surrounds the main disk. From this new perch, the view would be unlike anything a human has ever witnessed. Imagine looking back at the galactic core. You would see not the gentle milky band we see today, but a roiling, chaotic sphere of light shot through with the brilliant blue fire of the starburst regions and crisscrossed by dark lanes of dust. 2 galactic centres not yet merged would orbit each other in a fiery dance, each surrounded by a swarm of billions of stars. The sky would be filled with new, unfamiliar constellations populated by stars that were once citizens of Andromeda. We would be immigrants in a new celestial country, our Sun, a refugee of the Milky Way, finding its place in the grand merged metropolis that future astronomers have already poetically named Milkomeda. Life on Earth, assuming it survives our Sun's own evolution, would continue under a sky transformed, a constant luminous reminder of the violent creative upheaval that gave our galaxy its new form. We would be safe, but we would be adrift on a new and wilder cosmic sea. And yet the gravitational drama of the stars and gas clouds, as spectacular as it is, pales in comparison to the main event. For this entire saga, this multi-billion-year story of approach and merger, has been building toward a final singular confrontation. It is a clash of the titans, an encounter between the 2 most powerful and enigmatic objects in their respective galaxies. Deep in the heart of the Milky Way, hidden behind impenetrable veils of gas and dust, lies Sagittarius A, our central supermassive black hole. It is a monster 4 million times the mass of our Sun, a gravitational anchor around which our entire galaxy revolves. For eons it has been a sleeping giant, feeding only on the occasional star or gas cloud that wanders too close. And 2.5 million light-years away at the core of Andromeda lurks an even greater beast. A supermassive black hole weighing in at over 100 million solar masses, its gravitational dominion absolute within its own galactic empire. These are the 2 gravitational hearts, the dark sovereigns of their domains. And as their galaxies merge, they too are set on an unavoidable collision course. The process will not be swift. As the 2 galactic cores begin to orbit each other, The two black holes are carried along with their attendant star clusters. At first their dance is wide, taking millions of years to complete a single orbit. But with every pass they shed orbital energy through a process called dynamical friction. They fling away nearby stars, transferring their momentum to them, and in doing so sink ever closer to one another. The stellar waltz becomes a death spiral. The distance between them shrinks from light years to light months to light days. The final stages of this merger are a spectacle of physics at its most extreme. As these two space-time singularities, these 2 points of infinite density whirl around each other at nearly the speed of light, they are no longer just disturbing the stars around them. They are stirring the very fabric of space-time itself. They become the most powerful gravitational wave generator in our local universe. Ripples in reality, distortions of space and time propagate outwards from their violent dance, carrying away colossal amounts of energy. This is the universe's way of announcing a truly cosmic event, a silent scream that travels across the cosmos at the speed of light. And then, after a spiral that has lasted for hundreds of millions of years, the moment finally arrives. The two event horizons touch. They merge. In an instant, the two black holes cease to be separate entities. They become one. A new, even more massive black hole is born at the heart of Milkomeda, the quiet king of a new galactic empire. The resulting gravitational waves from this final coalescence would be so powerful, they would briefly outshine the light of every star in the merged galaxy combined. But this explosive birth is not the end of the story. It is the beginning of the final act. The merger of the two galaxies has done more than just bring the two black holes together. It has catastrophically disrupted the stable, orderly orbits of the billions of stars and immense gas clouds that once circled them at a safe distance. A torrent of new fuel, a river of interstellar material that has been violently shaken loose by the galactic collision, now begins to pour down towards the newly formed central monster. For a time, the sleeping giant awakens, and it awakens with a fury that will reshape the very heart of the new galaxy. As this maelstrom of gas and dust spirals into the black hole's accretion disk, it is compressed and heated to unimaginable temperatures, millions of degrees. The disk begins to glow with an intensity that beggars description, shining with the light of 1 trillion suns. From the poles of the black hole, powered by twisted magnetic fields, 2 colossal jets of energy and matter are unleashed. These are relativistic jets, particles accelerated to 99.9%. The speed of light, a pair of celestial blowtorches that will punch clean through the new galaxy and extend for hundreds of thousands of light years into intergalactic space. The heart of Milkomeda has become a quasar, an active galactic nucleus. It is a temporary transformation, a final, brilliant roar celebrating the merger. For a few million years, our galactic core will become one of the brightest objects in the known universe, a beacon visible to any emerging civilizations in galaxies billions of light years away. This intense sterilizing radiation will scour the central regions of Milkomeda, evaporating the atmospheres from any nearby planets and shutting down star formation in the core for good. It is the galaxy's final violent convulsion, a period of intense activity that cauterizes the wounds of its own formation. Eventually the supply of fuel will run dry, the torrent of gas will dwindle to a trickle, and the quasar will sputter and die. The jets will fade, the accretion disk will dim, and the supermassive black hole will return to its quiet slumber. The chaos will subside, the starbursts will burn themselves out, the gravitational fireworks will cease. What's left is a new reality, a single massive and fundamentally different galaxy born from the union of 2 spirals. The age of violent creation is over. A new, more settled epoch has begun. The question that hangs in the quiet aftermath is, what kind of home have we inherited? What is the ultimate fate of this new island universe? This Milkomeda now drifting alone in the cosmic dark. Out of the multi-million-year firestorm, a new silence begins to descend. The celestial violence, the raw gravitational fury that we have witnessed does not simply cease. Instead, it transforms its cacophonous roar, slowly fading into a deep resonant hum that will shape the destiny of 1 trillion suns. The 2 great rivers of stars, once separate and majestic, have now fully overflowed their banks, their currents irrevocably mixed. But at the heart of this swirling incandescent chaos, two immensely powerful gravitational anchors remain. The supermassive black holes that once commanded the centres of two galaxies, our own Sagittarius A and Andromeda's colossal heart of darkness, are now locked in a final inescapable gravitational embrace. They have been spiralling towards this moment for millennia, shedding incomprehensible amounts of energy as gravitational waves ripples in the very fabric of space-time that have been broadcasting the story of their deadly waltz across the universe. In these final stages, their dance becomes a maelstrom. Stars that wander too close are not merely consumed, they are seized and flung away with terrifying velocity, ejected from the nascent galaxy altogether in a process of gravitational slingshotting. These become hypervelocity stars, lonely exiles destined to journey forever through the deepening void between the galaxies of the local group. They are the final desperate sacrifices offered to the union of these two titans. The space around the galactic core is cleared, scoured clean by their lethal proximity, creating a sparsely populated zone around the two deadliest objects in the cosmos. As they draw closer, their orbital speed approaches the speed of light itself. Time and space warp violently around them, a cosmic whirlpool stirring reality. From our distant future vantage point, we would see a gravitational lensing effect of impossible complexity as the light from background stars is bent and distorted around these 2 points. Then in a final cataclysmic instant that lasts less than a second, they touch. The two event horizons, the points of no return, merge into one. It is not an explosion in the way we understand it, not a burst of light and matter, but something far more profound. It is a convulsion of space-time itself. A burst of gravitational waves more powerful than all the starlight in the visible universe erupts from the merger, carrying away the equivalent of hundreds of solar masses of energy. This is the birth cry of a new monster. A single, unified, supermassive black hole weighing perhaps 150 million times the mass of our Sun now sits enthroned at the centre of the new reality. For a moment, this newborn behemoth is misshapen, distorted by the violence of its creation. It quivers, ringing like a struck bell, shedding the last of its deformities, as more gravitational waves before settling into the perfect lethal sphere of a Kerr black hole. This new gravitational sovereign is now the undisputed ruler of the galaxy we will call Milkomeda. Its reign will be long and its influence absolute. Everything from the most distant star to the closest orbiting dust will now follow its command, its immense gravity the anchor for everything that is to come. With the central engines now unified, a different kind of quiet begins to spread. The great starbursts, the furious stellar nurseries ignited by the collision, are starting to burn themselves out. For millions of years, the compression of vast interstellar gas clouds turned our merging galaxies into a celestial forge, blazing with the brilliant, short-lived light of tens of thousands of massive blue stars. We saw nebulae glowing with ferocious intensity, stellar winds, carving vast bubbles in clouds of hydrogen and helium, and supernova explosions peppering the galactic disk like strobing fireworks. It was a golden age of creation, frantic and beautiful. But such intensity cannot last. The fuel for this fire, the free-floating gas and dust, has been almost entirely consumed. What wasn't ignited into stars was blown away by their radiation, or consumed by the black holes. The forge is growing cold. Across the immense canvas of the new galaxy, we see the change in its very colour. The vibrant blues and purples of young hot stars begin to fade from the palette. The stellar factories are shutting down one by one. The stellar winds die down, the glowing nebula dim, and the rate of supernovae dwindles. The galaxy is exhaling its last creative breath. What remains is the light of longer-lived stars, the yellows, oranges, and deep reds of suns like our own, and the ancient crimson glow of red giants. The character of Milkomeda is fundamentally shifting from the energetic, chaotic blush of youth to the serene, stately grandeur of old age. It is a transition that takes hundreds of millions of years, a slow, majestic sunset on a galactic scale. The era of spiral arms, of dusty lanes obscuring brilliant nurseries is over. The era of the great elliptical has begun, and it will be defined not by birth but by memory. This new cosmic city will be built almost exclusively from pre-existing structures. There will be precious little new construction for billions of years to come. and as the light settles, the new form finally resolves itself. The elegant pinwheeling disks of the Milky Way and Andromeda are gone. They have been utterly and completely erased from the cosmic record. Imagine taking two exquisite spinning plates of glass each, with intricate spiralling patterns, and shattering them together into a cloud of fine dust. The individual patterns are lost forever, replaced by a randomized shimmering whole. This is what has happened to the stars. During the merger, each star was pulled and torqued by the tidal forces of the passing galaxies. Their neat, orderly, nearly circular orbits within the galactic disks were violently disrupted. They were thrown high above and far below the old galactic plane, their orbital momentum scrambled by countless gravitational encounters. The result is not chaos, but a new kind of order. A sublime three-dimensional order. Milkomeda is an elliptical galaxy. It possesses no defining disk, no spiral arms, no central bar. Instead, it is a vast, shimmering spheroidal cloud of 1 trillion stars. From the outside, it would appear as a smooth, featureless globe of light, brightest at its core, and gently fading into the blackness of intergalactic space. It is a far simpler, more primal shape, a testament to the randomizing power of gravity. The internal dynamics are a universe away from what we knew. Life in the Milky Way was like living in a city with perfectly circular one-way streets. Everyone moved in the same direction at roughly the same speed in a flat plane. Life in Milkomeda is like living in the centre of a swarm of 1 trillion bees. Stars now move on highly eccentric, elongated, and randomly inclined orbits. A star might spend 1 million years plunging directly toward the galactic core, only to be whipped around the central black hole and flung far out into the halo, climbing for millennia, before gravity halts its ascent and pulls it back in. Every possible orbit is represented here. There is no prevailing direction, no cosmic rush hour. There is only the ceaseless, majestic, three-dimensional dance of stars around a common centre of gravity. This is the ultimate resolution of the collision, the complete randomization of stellar motion, settling into a state of gravitational equilibrium known as virialization. The system has found its final, most stable configuration. For any descendants of humanity, should they have survived this immense journey, the view would be utterly alien. The Milky Way's faint, beautiful band, a river of light that graced our ancestral skies, is gone. You can no longer look in one direction and see the dense core of the galaxy, and in another to see the sparse outer rim. The sky is now filled with stars in every direction. The stellar density, especially if our sun has settled into an orbit closer to the core, would be dramatically higher. Night would not be black, but a deep star-dusted twilight illuminated by the collective glow of hundreds of thousands of nearby suns. The familiar constellations, the signposts of our history, would have been obliterated. Every star in our sky would be a stranger, their positions utterly reshuffled. We would be adrift in a new cosmic sea, our old maps useless. The sun's own journey through this new metropolis will be a path of soaring climbs and daring plunges, a celestial roller coaster lasting hundreds of millions of years per circuit. We may pass through regions of incredible stellar density, navigating a glittering fog of ancient red dwarf stars before being cast out into the lonely, quiet frontiers of the galactic halo. The galaxy is no longer a place we inhabit on the periphery. We are now and forever part of its very heart, its very substance, no longer suburbanites, but denizens of the core of a megalopolis. This colossal new entity, Milkomeda, stands as a monument. It is a monument to the relentless, patient power of gravity. It is a monument to the two magnificent spirals that gave their lives to create it. Within its vast golden halo, the constituent parts are still there but forever changed. The ancient globular clusters that once orbited the Milky Way and Andromeda still trace their paths through the new galaxy, like ghosts remembering an old kingdom. They are the oldest witnesses, the survivors who saw the two galaxies in their prime and now watch over their unified descendant. The central bulge of the Milky Way and the core of Andromeda have merged their stars, blended into a single brilliant nucleus that outshines everything around it. The stars from our own spiral arm, the Orion arm, are scattered across tens of thousands of light years, their kinship forgotten, their shared history dissolved into the stellar sea. Our sun is just one of 1 trillion anonymous citizens in this new galactic empire. what we are witnessing is a fundamental process of cosmic evolution. Across the universe, we see these giant elliptical galaxies, these silent reddish behemoths that dominate the centres of galaxy clusters. For a long time, their origin was a profound mystery. They seemed so different from active star-forming spirals like our own. Now we understand. They are not born this way, they are made. They are the products of titanic collisions, the graveyards of spiral galaxies. They are the final mature state for a huge fraction of the universe's mass. Milkomeda will join their ranks, another majestic golden orb in the cosmic tapestry. It is the end of a story that began billions of years ago when two galaxies were first set on an unstoppable collision course. The drama of their approach, the violence of their merger, the brilliance of their star-forming death throes, all of it has led to this. A single grand and quietly magnificent elliptical galaxy, drifting serenely through the cosmos. It is the ultimate resolution, the final chord in a symphony that spanned eons. The new entity is stable. It is settled. It is for all intents and purposes complete. Its future is one of slow, predictable decline, a gradual fading over trillions of years as its last remaining stars exhaust their fuel one by one. The era of dramatic change is over, but in this final settled form there is a kind of profound peace. The struggle has ended. The union is complete. The Milky Way and Andromeda are no more. In their place stands something larger, something older in character, something that carries the legacy of both within its trillion-star embrace. And we are now part of it. Our destiny is now inextricably linked to this new cosmic giant. The question that remains as we drift through this unfamiliar star-drenched sky is what that destiny will be. What does the universe have in store for this new creation, and for the tiny flecks of life that have ridden the storm out within it? The great crash is over, but a new, far longer and much quieter journey has just begun. And so, the celestial ballet reaches its final magnificent apotheosis. The two great spirals, once separated by an ocean of darkness, have become one. Before our eyes, born from gravitational fire and stellar chaos, a new cosmic empire has been forged, Milkomeda. This colossal elliptical galaxy, a shimmering golden haze of ancient stars, hangs in the simulated void as a testament to the most fundamental force of creation in our universe. It is the inevitable, spectacular, and strangely serene destiny of our home. Our journey to comprehend this future has been a pilgrimage through time itself, a story not just of galaxies, but of the human spirit's relentless quest for understanding. We began this story as our distant ancestors did, looking up at a faint fuzzy patch of light in the constellation of Andromeda. To them it was a mysterious cloud, a celestial nebula woven into myths of chained princesses and sea monsters. For millennia it held its secrets close, a silent enigma in the celestial tapestry. We travelled forward through the centuries, standing alongside astronomers in their cold, lonely observatories, witnessing the moment that small cloud was first seen through a telescope, its true nature still tantalizingly out of reach. We felt the seismic shift in perspective when in the early 20th century a new generation of titanic telescopes and photographic plates finally captured its stunning truth. The revelation that Andromeda was not a cloud within our own galaxy, but an entire island universe in its own right, utterly shattered our conception of the cosmos. In that single discovery, the known universe expanded 100,000-fold, and humanity for the first time truly began to grasp the sheer, terrifying scale of reality. From that monumental realization, our investigation deepened. We learned to decipher the language of light, a cosmic code carried on photons that have travelled for 2.5 million years to reach us. We saw in its subtle blue shift the first clue, the startling evidence that this colossal galaxy was not drifting away from us, as nearly every other distant galaxy is caught in the universal tide of cosmic expansion. No, this one was different. It was falling toward us, a gravitational inevitability set in motion billions of years ago. This discovery transformed Andromeda from a beautiful static celestial object into a dynamic protagonist in our own future history. It gave our Milky Way a partner in a cosmic dance, a final, unavoidable rendezvous. Our quest then led us to the frontiers of technology, where the vast, intricate simulations we have witnessed were born. Here in the digital hearts of supercomputers, we compressed billions of years into mere moments. We fed these virtual universes all the physics we could muster, the stubborn grip of gravity, the mysterious scaffolding of dark matter, the explosive lives and deaths of stars. We watched as no human ever will the first delicate tidal fingers stretch out between the two galaxies, a gravitational handshake across 250,000 light-years. We flew through the resulting chaos, a time of unprecedented celestial fireworks. We saw vast streamers of gas and dust torn from their galactic moorings, igniting in a final glorious burst of star formation, painting the darkness with the brilliant blue light of countless newborn suns. These simulations are our crystal ball, our only portal to this deep future. They are the culmination of every observation, every theory, every painstaking calculation that came before. They represent the pinnacle of our ability to ask the universe what if, and receive a coherent, breathtaking answer. This journey from ancient myth to computational oracle mirrors our own species' evolution. It is a testament to our insatiable curiosity, our refusal to accept the darkness as an impenetrable veil. We have in essence written the biography of a future we will never see a story etched not in ink, but in the fundamental laws of the cosmos itself. Now let us linger here in that far-flung future and contemplate the nature of what has been created. Milkomeda is not simply the sum of its parts. It is a new entity, a different kind of celestial being altogether. The beautiful swirling spiral arms of the Milky Way and Andromeda are gone forever. Those grand star-forming rivers of gas and dust, the celestial nurseries where generations of suns were born, have been exhausted. The titanic collision compressed them, ignited them, and ultimately consumed them in that final galaxy-spanning starburst. What remains is a vast, serene, and hauntingly quiet sphere of light. Milkomeda is an elliptical galaxy, a cosmic elder statesman. Its light is not the brilliant, vibrant blue-white of youth, but the soft golden-red glow of ancient long-lived stars. Trillions of them, each locked into a new randomized orbit like a swarm of bees buzzing within a colossal invisible gravitational hive. The coherent disk-like rotation that once defined our galaxy is now just a memory, a celestial ghost haunting the chaotic motions of this new stellar metropolis. At its heart, an even more profound transformation has occurred. The two supermassive black holes, Sagittarius A from our Milky Way and its far larger counterpart from Andromeda, spent millions of years spiraling toward one another in a deadly gravitational embrace. As they drew closer, they warped the very fabric of space-time around them, flinging away any stars that dared to pass too near in a process called gravitational friction. Their final merger would have been the single most violent event in the history of our local group, an explosion of gravitational waves, ripples in reality itself, that would have radiated outwards at the speed of light, carrying with them the energy of millions of exploding stars. The resulting single supermassive black hole, a behemoth with the mass of over 100 million suns, now sits as the undisputed silent monarch on the throne of Milkomeda. It is the new gravitational anchor for trillions of stars, the dark heart around which this new galactic empire will revolve for eternity. Life as we know it, or any life that might have arisen in our galaxy, faces a profoundly different future. The era of rampant starbirth is over. With the free-floating gas and dust used up, the galaxy's creative engine has sputtered to a halt. Future generations of stars, and with them the potential for new planets and new life, will become vanishingly rare. Milkomeda will be a galaxy of endings, not beginnings. A quiet, majestic mausoleum of stars slowly, gracefully burning through their remaining fuel. Any civilizations that might survive the merger and endure for eons would look up at a sky both more crowded and more static. The river of the Milky Way, that beautiful band of light that has inspired wonder for all of human history, will be gone, replaced by a more uniform, diffuse glow in all directions. It would be a sky of ghosts, a sky filled with the last embers of a fire that once raged across two magnificent galaxies. This is the ultimate fate we have uncovered, our home transformed into a tranquil, colossal, and profoundly lonely cosmic artifact. And yet this story, Our story is not an isolated event. The creation of Milkomeda, as monumental as it is but a single brushstroke in a much larger cosmic masterpiece. To truly grasp its significance, we must pull our perspective back even further. The Andromeda Milky Way collision is merely the most dramatic chapter in the life of our immediate cosmic neighbourhood, the local group. Other smaller galaxies like the Triangulum Galaxy and the Magellanic Clouds are also part of this gravitational dance. Many will eventually be consumed by the new Milkomeda, their stars and dark matter added to its ever-growing mass over hundreds of billions of years, like small streams flowing into a great ocean. Our local group is in effect collapsing under its own gravity, consolidating its matter into one final gargantuan structure. This process of galactic cannibalism of mergers and acquisitions is not an anomaly. It is the primary way the universe builds structure. It is the cosmic engine of evolution. Everywhere we look with our most powerful telescopes out into the depths of space and time, we see this story repeating itself on every scale. We see small irregular galaxies merging to form the first spirals. We see spirals like our own colliding to forge giant ellipticals. We see entire clusters of galaxies containing hundreds or even thousands of members, all drawn together by their mutual gravity, a cosmic pile-up of unimaginable proportions. Our own local group is just one small suburb in a much larger supercluster of galaxies, the Virgo supercluster. And even this immense structure, this cosmic city of over 1,000 galaxies, is not stationary. It is being pulled inexorably toward an even larger concentration of mass, a mysterious gravitational anomaly we have nicknamed the Great Attractor. This process, gravity pulling matter together on ever larger scales, is in a constant epic battle with the universe's other great force expansion. Since the Big Bang, the very fabric of space-time has been stretching, carrying galaxies apart from one another. For now, in our local corner of the cosmos, gravity is winning. It is strong enough to overcome the expansion to pull our local group together to ensure the eventual creation of Milkomeda. But on the grandest of scales, the scales of the entire observable universe, gravity is losing the war. This brings us to the final and perhaps most profound chapter in the story of our galactic home. What is the ultimate fate of Milkomeda in this ever-expanding universe? As it ages, as its last stars exhaust their fuel and fade to black, it will face a future of profound and deepening isolation. The cosmic expansion is not just constant, it is accelerating, driven by a mysterious force we call dark energy. As the eons pass into trillions of years, this acceleration will become utterly dominant. Every other galaxy group, every other supercluster not gravitationally bound to us will be pushed away at ever-increasing speeds. They will eventually recede from us faster than the speed of light, their light stretched to invisibility, their presence erased from our sky. They will cross a cosmological horizon forever beyond our reach, beyond our observation. The universe as seen from within Milkomeda will become a terribly empty place. The sky will be dark, save for the faint red glow of our own galaxy's dying stars. All evidence of a larger cosmos, of the Big Bang, of other island universes will be gone. Future astronomers, if any exist, would be forgiven for believing that their own galaxy was the entire universe, a solitary island of matter in an infinite eternal void. Milkomeda, born from a spectacular union, is destined to become the ultimate cosmic castaway. It will be a self-contained universe, a ship of aging stars sailing into the endless night of an ever-emptying ocean. This is the endgame. The slow, quiet fade into the era of cosmic heat death. The stars of Milkomeda will one by one wink out, becoming cold, dark remnants, white dwarfs, neutron stars and black holes. Even these will not last forever. Over timescales so vast they beg a description, quantum mechanics predicts that they too will evaporate, their matter converted back into faint radiation. Eventually only the central supermassive black hole will remain, and after an unimaginable length of time it too will radiate away into nothingness. All that will be left of our brilliant Milky Way, of the majestic Andromeda, of the golden empire of Milkomeda, is a silent, cold and featureless void. The story of our galaxy will finally truly be over. So where does that leave us, you and I, here and now? We find ourselves living in a privileged moment, a fleeting, precious window in cosmic history. We live in a universe still young enough, still vibrant enough to be filled with the light of 1 trillion galaxies. We live in an era of brilliant star formation, a time of creation and possibility. And most remarkably, we live in a moment when the human mind has for the first time pieced together this entire epic story. From the first spark of the Big Bang to the final quiet, fade to black. The fate of our galaxy, a collision set to occur 4.5 billion years from now, will never be witnessed by a human eye. Our species, our planet, even our sun will likely be long gone. And yet we can see it. We can understand it. We can feel a sense of awe for its terrible, beautiful grandeur. The knowledge of this deep future does not diminish our present. It enriches it. It lends a profound cosmic perspective to our transient lives on this small, fragile world. We are the universe's way of knowing itself. We are the witnesses. The story of the stars is our story, for we are made of their dust. And the story of our galaxy's collision with Andromeda is a reminder that we are part of a dynamic, evolving, and utterly magnificent cosmos. A universe not of static perfection, but of endless, breathtaking change. A grand cosmic ballet choreographed by gravity playing out over billions of years, and we for one brief shining moment have been granted a seat to watch it all unfold.